Okay, so we will continue with problem 7. We have a wheel A that provides intermittent motion omega A for continuous motion omega D of disk D. By choosing D equals to radical 2r, the wheel has zero angular velocity at the instant pin B enters or leaves one of the four slots. Determine the magnitude of the angular velocity omega A of the wheel A when theta equals to theta 1 so that pin B is in contact with the slot. In this problem, we have two wheels, okay, but one have continuous rotation. So this wheel is rotating with omega D clockwise equals to 2 radian per second. While here your wheel A is not of circular shape, okay, as you can see here, you have four slots in this wheel. And what is happening is that you have a point B of the disk D that can translate relative to wheel A. So it can go back and forth. Okay, so as you can see, B will go back and forth, then rotate like this, then it will enter a new slot, etc. Okay, now in this problem, we want to just determine the magnitude and the angular velocity omega A when theta is equal to 30 degrees. And in this case, pin B is in contact with the slot. So B at this instant is within the slot. So first here in this problem, as usual, okay, we have two motion. We have motion of disk D and we have motion of disk A. And we want to try to correlate them because we know completely the information about disk D. We know omega D equal to a constant. So we can deduce that alpha D is 0. So for disk D, everything is known. Now, concerning the second wheel, okay, we just need to relate its motion with the motion of D. And as you can see here, wheel D position is given by angle theta. So what we should do, we should try to relate the angle theta to the angle of rotation of wheel A phi. And another parameter that is important is the distance. B is moving along the slot as we said. Okay, so here at a certain instant, we will have this point within the slot. Okay, so we will try to find the coordinate of SB function of the other parameters. Okay. Now, to do so, if we look at our figure, we already can form a triangle. This triangle is this one. So here from the center to the center, this is a fixed length D. D equals to radical 2r. Okay? And we have that this distance is fixed because B is fixed on the wheel, but SB is varying since B can translate in the slot. Okay? So now, the first relation that we can write is by considering the following figure. In particular, we have that this distance is given. The distance separating the 2 points here is given. Okay? This distance is equal to radical 2r and it's fixed. So I can say that this distance can be decomposed into two parts. Because if I project the position of B on this horizontal line, I can say that it can be divided into two parts. The first part is r cosine theta. So this length here will be r cosine theta. And this distance will be depending on phi and on the position of B, S of B. Okay, so this distance is S. They called it here BA, SBA. So this is SBA cosine phi. So this is a geometrical relation relating our parameters, which are theta, phi, and S. Okay. Now, this is a first relation. Whenever I get a geometrical relation, in order to relate angular velocities, I should derive with respect to time. So now I derive this relation with respect to time. So I get the following. We know that R is constant because it's the radius of wheel B. Cosine theta is function of theta. So when I derive with respect to time, I will use the chain rule. So I will have minus R sine theta times omega d. Okay? Then, for the second term, when I derive the second term, I have two variables because S is varying and V is varying with time. So it's like U times V. So when I do the derivative of U times V, it's U prime V plus UV prime. U prime constitutes the velocity of B relative to the slot, S prime, okay, times cosine phi plus UV prime. Now for V prime, I derive cosine phi with respect to time. It is minus sine phi, and I don't forget to multiply by d phi by dt to apply the chain rule. And d phi by dt is simply omega of disk A. Okay? So in this way, by deriving a first time with respect to t, I got equation 2, which will relate S dot and omega A to the other variables. Okay? Now, how to proceed? You know that these relations are not enough, because you have several unknowns. Let us state our unknowns. What are our unknowns? We just know theta. So if our inputs are theta and omega. Okay. Now our unknowns will be, so knowing theta and omega, we should be able to determine what is phi, what is S, what is phi dot, so what is omega A if you want, and what is S dot. We have four unknowns. Okay, we have already written just two relations, so we need other two relations to close the system. This is why we should try also to find geometrically another relation. Always when you have a triangle, think about the sine law. Okay, because if you look at your figure in this triangle here, you can apply the sine law. You can write that this length, which is S, SBA, over sine of this angle, which is theta, over sine theta, is equal to this distance, which is R, the radius of the disk, over sine phi. So equals to R over sine phi. This relation is equation number 3. So as you can see now, by combining equations 1 and 3, 1 and 3 will give you two equations with two unknowns, which are phi and SB relative to A. So you can solve for these two. Now, in order to get another relation involving angular velocities, we should derive another time with respect to time. Okay? So now the sine law, we will derive it with respect to time to get a fourth relation. So as you can see here, we have the sine law will give us, so this is sine law, we have r sine theta equals to s sine phi. Now we will derive it with respect to time. So first, r is constant. So the derivative of r sine theta is r cosine theta times omega d, where omega d represents theta dot. Okay. Now for the second term, you have s times sine phi. So it's like u times v. So when you derive u times v, it's u prime v plus v prime u. And then you can say that the derivative of SVA is S prime BA, so U prime times V, plus the derivative of sine phi using the chain rule is cosine phi phi dot, which is omega A. So this is equation number 4. And now, if you combine 2 and 4, you will have 2 equations with 2 unknowns. After finding from 1 and 3, so 1 and 3 will give you the unknowns s and phi. So you combine these two to find s and phi. And once you find s and phi, you replace into 2, 4 to get omega A and s prime. And now in particular, this is general system. You can apply it for any position you want. So here I ask for theta equal to 30 degrees. So you just replace theta by 30, you get the corresponding s phi. And replacing s phi in 2 and 4, you get the corresponding angular velocity of wheel A and velocity of point B relative to the slope. Okay? Any question on this? Okay. Another problem. A ride in an amusement park consists of a rotating plate P having constant angular velocity omega p and 4 cars C mounted on the plate which have constant angular velocities omega cp measured relative to the plate. Determine the velocity and acceleration of the passenger at B at the instant shown. In this problem, you can think in several ways. Okay? So let us do the analysis together. First, what do we have? We have a big plate P. This big plate is characterized by a certain angular velocity omega p. And we have that the 4 cars are moving relative to the plate at a certain angular velocity omega c relative to p. Okay? So you can say, if you want, if I take each car separately, so what will be the total angular velocity of each car? Each car will have as total angular velocity omega c equals to omega p plus omega c relative to p. So for the angular velocities, they can be added. Okay? If you know omega of the plate and you know the relative angular velocity of a body with respect to the plate, you can say that the total angular velocity of any of the cars is vector omega p plus omega c relative to p. Here, as you can see, both are along positive k because both are counterclockwise. Okay, so in total, we have omega p, we have omega cp. So we can say that vector omega c is equal to 1.5 plus 2 equals to 3.5 k. Now, the question is to determine the angular velocity of point B, this one. Okay, this point. This is our purpose. Okay, now In order to find the angular velocity of this point here, we want to try to relate it to another point of the car of known velocity. Okay? In particular, so if you look at your figure, this point here, the center of the car, you can calculate its velocity. The center of the car is on the axis of rotation of the car. Okay? So the velocity of this point is not depending on omega Cp, because if you consider a body rotating about its axis, okay, all points relative to this axis will move, just this point will be fixed. Okay, we'll have a velocity of 0 in case it's not on a moving body. Okay, so this point will not be affected by the rotation of the body relative to the axis. This point will only have a velocity here due to what? Due to its position on the plate, because this car is placed on the plate. So the plate will give it, as the plate will rotate, the center of the car will rotate with it. Okay? If the plate was fixed, then the center will be fixed. This is how you can think. If the plate is fixed, the center will be fixed. If the plate will rotate, the center will rotate. So the velocity of this point is affected by the angular velocity of rotation of plate P. And I can easily calculate its velocity because this is a circular motion. In circular motion, the velocity should be perpendicular to the radius. So if I call this point O, I can just say that velocity of O is equal to omega P times this distance, the distance from P to O, okay, which is named here R. This is R, okay? So it's omega P times R, and as a vector, it's vertical, so it's omega P R along J. So now I know the velocity of the center, okay, and I know the total angular velocity of the body, omega of the car is equal to 3.5 k. All I have to do is to relate now points B and O. So I can just say that because B and O are 2 points of one rigid body, I can write that velocity of B is equal to velocity of O plus omega of the car absolute, the total angular velocity of the car, vectorial OB. So now if I replace, this is what they did here, guys. Look, here, this term is velocity of O. How we get velocity of O? Now we did the method of magnitude and the right-hand rule. Then they did to find VO, they did the vectorial method. If you want to do the vectorial method to find VO, VO is Vp, which is 0 because P is fixed, plus omega of the plate vectorial PB. So this term, this is omega P vector, and this is vectorial PO. And vector PO is along I. Okay, so look, this in this representation, omega P is along K, so the vector will be 0, 0, omega P. PO is along I of magnitude R, so it's R, 0, 0. If you do the vectorial product, you will obtain the following, omega PR J, as we did in the second method. Now plus omega car, which is along K, and it's equal to omega, it only has a component along K, so it's 0, 0, omega P plus omega CP, vectorial vector OB. And OB vector is directed along I, so it has only a component along I, so it's small ri, 0j, 0k. Okay? Now, if you do the expansion, you can get your velocity vector, and of course, you can get its magnitude and direction. Here, from the result, it's clear that VB is only about J, and you can expect this because VO is vertical, and also the relative velocity of B with respect to O is vertical. And B is rotating with respect to O. So now you will add two vertical vectors, which will give you a vertical component on G. Now, another method is to do the rotation motion. We use the relative motion with axes that are rotating. Why we can do it here? Because look, you have B is on a rigid body that is rotating relative to another frame. Okay? So if you remember when we talked about the vectorial relation of rotation, what did we said? We said that we use it in general when we have a body that have freedom of motion with respect to another body. This is the case here. You have this disk is free to rotate on another disk, another rigid body. Okay? So how we can do the rotary analysis, rotary motion analysis in this problem? First, you have the main rigid body is plate P. Plate P is rotating. So what you can do, you can take ij, small I, small j, fixed to the big plate. Okay? So small I, small j will represent the frame that will rotate with the plate. It will rotate at an angular velocity of omega p. And B is having a relative motion with respect to the plate, which is due to its relative rotation around the center of the core. So what can you write then? If you use the formula of rotating axis, you can say that I will relate point B to point P, which is the center of the rotating axis. And I can write that velocity of B is equal to velocity of point P plus, now which omega I will use? I will just use omega of the rotating frame. Here, the frame is rotating with the plate, so I will just use omega P. So plus omega P vectorial PB, and I should not forget to add what here? I should add V relative plus V relative. Okay? Now let us see together what are our different components. To start with point P, P is fixed, so Vp is 0. Now, we can write then that Vb is equal to omega P. Omega P is 1.5K. 1.5K. Vectorial. Vector PB, as you can see here, vector PB is equal to vector PC plus CB. So it can be written as big R plus small r along I. And finally, plus V relative. V relative represents what? It represents the relative motion of B with respect to the plate. So if you are standing on the plate, what do you see? You see that B is doing rotation about this point. Okay? So if you are standing here, this point seems fixed to you, but B is rotating about it. So V relative is due to the rotation of B around this point. So you can get V relative by just doing omega C relative to P, which is 2 radians per second. So plus 2K vectorial OB, and OB is small r times I. If you do the addition, you will go back to this formula again. You will go back to the same expression. Okay? If you want to expand more, I can do it. If it's not clear, I will repeat. Okay. So now, the next step is to calculate the acceleration of the passenger at B. Okay? So to find the acceleration, also same method. Okay? You have two possibilities here also. Or we go to the first approach. We find alpha total. Okay? So alpha total here of car C vector is equal to alpha p, which is 0 because omega p is constant, and also alpha cp is 0 because omega cp is a constant. So we can say here that no angular acceleration, alpha c is 0. So now if we replace into the vectorial relation, we have the vectorial relation states that by relating B, we are relating B to this point, okay? So acceleration of B is equal, this is point O, is equal to acceleration of O. Now how to calculate acceleration of O? O is doing what? O is rotating about P. So we can say that acceleration of O is equal to acceleration of P, which is 0 because P is fixed. So this is 0 plus alpha P vectorial PO, but also we have seen that alpha is 0 since omega is constant. So also this term will cancel out. So the only term that will remain is minus omega P squared times vector PO. And as I told you, this term in 2D is the same, is equivalent to omega P vectorial PO. Okay, but this is much easier for you to calculate. So this term represents AO. Now we should add to AO what? We should add, in this case, alpha total, okay, vectorial OB, but also we have seen that alpha total is 0. So this term will cancel out. And we just have the final term, which is minus omega total square minus omega total of C square times vector OB, where omega total is 3.5, yani 3.5 square times vector OB, which is along, so times Ri. And this is equivalent to this term, okay, اللي هو هيدا omega total vector. So this is omega C vectorial omega C vectorial OB. Okay, so at the end, using this procedure, you can calculate the acceleration of point B. Here, acceleration of B is just along I. You know why? Because tangential components are along J, but since alpha 0, you don't have tangential components. So you only have the normal components, which are along I. and it's along minus I directed towards the center. For B relative to O, it's directed towards O, and for O relative to P is directed towards P. So in total, you will have a negative component along I. Now you can try to practice with the equation of rotating axis. It should give you the same result. Okay, if you want, we can do it together. Do you want to do the acceleration form for rotating axis?
Yes, Dr.
Yeah, let us do it. Okay, let us do it. So if you want to use another method, okay, as we have seen before, we can say that we will take a rotating axis at P, okay? This is small I, small j, and we will write now the rotating axis formula, general formula, to get the acceleration of point P. Okay? So to start with, we have acceleration of B is equal to, first, what is the point of the rotating axis that we will relate B to? It's P. So it's AP plus alpha of the rotating frame اللي هي alpha P vectorial PB minus omega of the rotating axis اللي هي omega P. So minus omega P square times vector PB. لحديت هلا this term represent what? This is the acceleration of the coincident point. يعني إذا باخد البوينت اللي على البليت اللي coincident مع B هيدي الاكسلريشن تبعه. Okay? I should add to this the effect of relative motion. And as we have seen for acceleration في عنا two effects. في عنا الكوريوليس acceleration اللي هي 2 times omega of rotation omega P تبع rotating axis vectorial V relative اللي لقيناها in the previous step. Okay. Plus the only new term for us هو ال A relative. So we should add to this plus A relative. Okay. Plus A relative. Now what is A relative? يعني already AP is 0 لأنه P is fixed. Alpha P 0 لأنه قلنا أنه constant omega P constant. Omega P is given. Vector BP مثل ما قلنا PB is big R plus small r along I. V relative was calculated in the previous step. Okay, V relative is equal to the relative velocity of B with respect to the center of the car اللي هو omega CP اللي هي relative angular velocity times the small radius r along J. Okay, so we just still have to determine what is A relative. To determine A relative, we should go back to our figure. So the relative motion of B with respect to the plate is what? Is rotation about this point. صح؟ This is why قلنا أن relative velocity هي perpendicular للradius و V relative is equal in magnitude to omega CP اللي هي relative angular velocity. يعني إذا أنا واقف على البليت I will measure omega CP. I will see that B is rotating about its axis with an angular velocity omega CP وبقشع إنه هيدا الأكسس is fixed. بينما if I stand outside I will see the total angular velocity. So V relative equals to omega CP times the small r and it's along J. Now what about A relative? When we have rotation, we have two components of acceleration. We have A tangential, AT relative, and AT and AN relative, normal acceleration relative. Okay. Now, since here omega constant, so no tangential component, so AT relative is 0. لأنه AT relative is equal to what? It's equal to alpha CP, يعني relative acceleration of C with respect to P, times small r. But since omega CP constant, يعني alpha